So, welcome. Good morning, everybody. My name is Raghavendra Selvan. So I know you got lost after the first two syllables. So you can also stop then. So you can call me Raghav. I'm an assistant professor at the University of Copenhagen. I have dual affiliations for the computer science and at the neuroscience departments. So today's talk, I think in the program it just said graph learning. So I think we worked a bit more on that. And based on all the lectures that have gone on up until now, I've tried to modulate it a bit so that we have already come across graph neural nets on the first day, but to try and bridge some of the concepts which I think are very interesting for understanding graph neural nets. And that is what the title is. So I'm going to start something from a spectral theory point of view, and then we will end up with generalized message passing schemes. And this is sort of the context in which we are going to be looking at graph neural networks. All right, so the slides are at that link, because there's going to be some bit of math and then several footnotes. The slide again here. So if you want to download the slides while, if you're not able to see the, bottom of the screen or some such. All right, I think we are ready to go then. All right, so I think this is just a broad motivation. I don't think I'm going to get deep into this. You're all here because you want to do some bit of geometric deep learning, and then graphs are an essential part of non-Euclidean data. And they have been widely studied by now, within the context of deep learning. So we've looked at some applications with meshes on day one. Today, I'm going to focus a bit more on graph structure data that we encounter in other types of applications, for instance, in chemistry, and then I'll also have an example in biomedical imaging. So if that is not sufficiently motivating, so the number of papers which have graph neural net in their title is basically growing exponentially every year. Now, this doesn't mean you have to know about them, but perhaps they're also intersecting across different domains, and it's a good way to kind of understand what's happening with these models, with newer insights being gained from different perspectives. So this is sort of the general overview of my talk today. So I'm going to start out with a bit of the spectral graph processing. From there, we will arrive at one of the popular spectral graph neural net methods, which is the Chebyshev net. And going from there, we will arrive at the GNNs as we know, as the node propagating, neighborhood aggregating schemes. And then there's a bit of, I try to distinguish because there's like tons of GNNs by now, but just as a key difference, so there's two types that I would like to focus on with this talk, and each has like an application that I'm going to demonstrate with some of the work that we've done. And finally, to kind of connect with what we will see as generalized message passing, as to if we can connect it with belief propagation type of algorithms, or mean field approximation, and that's going to be the way this talk is going to proceed. And hopefully, we will have time to cover all that. So we'll start, in territories that we've been. So we've been looking at Laplacians, thanks to Andreas and Rasmus on day one. And we will start out there. So just to kind of, I've been talking, during lunch breaks, etc. So there seems to be a bit of, concern about what these Laplacians are. So, just to kind of maybe dumb it down, and then the geometric people maybe don't kill me out here, but just to kind of give you a bit of intuition. So if you are in Euclidean, one-dimensional functions, it's sort of like your second derivative, right? So you just get an idea of how smooth your particular function is, and then as you get into a Riemannian manifold, that's what the Laplace-Beltrami operator was. But what we are going to be interested in is discrete grids. So what happens, can we define these, what do you call, divergence of gradient operators, which are the Laplacians, on discrete data, such as graphs? And yes, we can, and they end up being very simple. So this is nice for us. So, a discrete graph Laplacian for any graph that is, defined by a set of vertices here, V, with a set of edges E. and defined by the adjacency matrix, which is the connectivity matrix. It could be weighted or unweighted. So what we end up with is this Laplacian, given as just a simple algebraic expression here, d minus a, and d is the degree matrix, which is basically a diagonal matrix. For a unweighted adjacency matrix, it basically tells how many connections a particular node has. So this is where we start. But going from here, so some of the ideas that we already explored on day one, we will try to see what happens when we map it to graph structured data. So that is, we want to look at the eigen decomposition of this Laplacian, and then look at what the eigen functions mean. So to be able to do that, we do a small trick, which is, we take the graph Laplacian, we normalize it by the, the degree matrix. So if you remember from the previous slide, how do I go? It was just d minus a, and we normalize it by the degree matrix. So you kind of take your d inverse and then multiply it on both sides, if you would like to think of it that way. So then what happens is like your d minus a expression. So d, and d inverse gives you an identity matrix. And going from there, we have the symmetric aspect. Now the symmetric aspect comes from here. So you have the d minus half and d minus half. So you kind of do a symmetric normalization. Once you have this Laplacian, I'm going to denote this symmetric normalized Laplacian as L. That can be decomposed into sort of your standard, orthonormal basis functions with another matrix here, which is your lambda. And the orthonormal basis, it is like you can think of it as your Fourier basis for a graph. And the lambda has the diagonal entries are the sorted eigenvalues. So what happens here is, so this is the Laplacian, and then now we have the orthonormal basis to take your any signal on your graph structure data into a Fourier basis. And so what does this mean for a classical Euclidean signal? Then you have like the low frequency components, which is your DC component, as we would call, and then you have, as you progressively move, you get the higher frequency components, and then the Laplace-Beltrami operator, which we saw on day one, so that you can also do a similar decomposition there. So you have the constant data, and then you do the same with graph structured data now. So you can have information, if you traverse the graph, then what information is moving, or constant, that is given by your phi 0 component. And then as you move to higher orders, so then the information as you traverse the nodes along the edges is going to increase or become more noisy or become high frequency. So why do we do this? Because we want to define convolutions. And here Eric was actually talking about how in CNN literature the convolution operation is more like the cross correlation, right? So but with graphs, initially the domain set out to define convolution as you define in signal processing. So as the like you take the kernel, and then you have a translating, and then you perform the signal processing way of performing convolution. But then there's no translation as such defined for if you want to move along the signal on a graph. So what do? We do the trick of going to the frequency domain. So that's where the whole concept of the spectral graph theory comes in. So we want to do convolution, but then in the spatial domain, it's not that nicely defined. So we move to the frequency domain. And to do that, what did we do? So in the previous slide, we had the orthonormal Fourier basis. So we take the signal and then map it to the Fourier space. And then we have the Fourier, the filter coefficients in the Fourier domain, and then it becomes a multiplication. Now, this is sort of the classical result from signal processing, right? Convolution in spatial domain is multiplication in sort of frequency domain. So we also have this decomposition of the Laplacian from before. Then if you compare this expression to this decomposition, what we end up is that your filter is basically just the eigenvalue function, the matrix with the eigenvalues. So now, of course, it's nice, but it has a couple of issues that It's non-local, meaning, this operation will operate for a given node. So you want like a filter, like a CNN filter, right? In Euclidean domain, you want it to operate on local data and so local regions. And with this type of a filter, it does not operate locally. It operates on sort of the full graph. So we don't want that. It's not that interesting. And it is also computationally expensive because this lambda here is obtained by the Laplacian eigen decomposition. And then if you end up with like large graphs, then this is computationally expensive. So we don't want to be doing this. So what do we do? So to alleviate the first point, we will see how this second problem is addressed later on. But just to make this, how do we make this non-localized filter localized? So I'm leading up to the Chebyshev paper, ChebyNet paper. I don't think they call it ChebyNet, but literature has by now changed that to ChebyNet. So instead of using just filter, which is this lambda, which was the diagonal matrix with all the eigenvalues, we work with polynomial parameterization of this lambda. So instead of taking just one filter, which was our lambda along with all the eigenvalues, we say that, okay, fine, we want to parameterize and then have more information here. So we try to work with these k polynomial filters. Now, what does this mean here? Okay, so we won't get too much into the details here, but by doing this, and because of this lambda raised to the power k, we can define neighborhoods which are local to k hops. So now if you think of it from a graph point of view, then we're talking about neighborhoods which are k neighbors away along the connectivity matrix. And this sort of, we're now in the territory of defining a locality, based on the node neighborhood. But of course, for this point, that is, it's super computationally expensive. We can't work with this. So we do a lot of approximations going forward. Some of it are really nice, and some you might think it's like too drastic. At that point, we will reach deep learning. So, and that's how it is. So the first trick is that if you remember from before, I don't have to change. So you have this, right? You have this lambda to the power k. Now you still don't want to be working with the matrix with eigenvalues, and then you having to, work with polynomials of that. So instead, we approximate that with a Chebyshev polynomial. So now this is where the trick. So it's an exponential, a polynomial term here, which we approximate with the Chebyshev polynomials. And to be able to approximate to the Chebyshev polynomial, the range here has to be, between -1 and 1, and that's all. So that it just gets a bit messy. But all we do here is basically take the eigenvalues and then normalize them to be in the range -1 and +1, so that we can then do the Chebyshev, polynomial expansion of that. So once this is done, what we do is plug this back into our convolution operation that we were initially seeking out, so that we can perform that on in the spectral domain. And that is, this is what we wanted, right? So we wanted to do the convolution in the spatial domain, and then we said, okay, that's not working. So we moved to the frequency domain, and then now we approximate that with a polynomial, filter, which is approximated using the Chebyshev. And once you plug this g theta using this expression, we no longer have to even compute the eigenvalue decomposition. So now your Chebyshev is a function of the Laplacian. So now this is a nice little trick, because doing the eigenvalue decomposition was going to be really cumbersome, but then the Laplacian is relatively cheap. Even multiplications are going to be expensive, but this is an easier way of getting out of it. Okay, so this is nice, and this is the ChebyNet paper. So where you can have like k spectral filters operating on your data, and then it's one of the, I think, most widely used spectral graph convolutional, filters. And in Rasmus's talk, he also mentioned that how the domain was moving away from graph neural nets being graph convolutional networks from spectral theory into something which is more like message passing. And I think I agree, but to be able to sort of look at there's a bit of elegance of starting out from the spectral domain and then dumbing it down so much that we become, do like neighborhood aggregation. But I think this insight is going to be important when you, look at like a lot of the graph neural net methods that are out there. So now let's get on to the next drastic levels of approximation. And this is, I'm basing, there are several ways, again, you can approach this, but I'm going to take up one of the works from my collaborator, Thomas Kipp, at also University of Amsterdam, where you start out with the Cheppy net, the spectral filter, but then you make two assumptions. One is that you don't want to go to like really large Ks, so you only want to work with K equal to 2. And what happens is like the Chebyshev polynomial expansion is a recursive one. So, and I think it's down here in the descriptions, but let's not get into that. I have some of the math for that. So with K equal to 2, we just end up with the first two components, right? And we also do another, this is not that important. So we scale the lambda max to be 2, and then we later say that, okay, we let the neural network figure out the balancing. So it doesn't matter. That was because if you see, we had this assumption here. So we wanted the data to be between -1 and 1, but then we wanted this lambda max. So now we scale lambda max to be, 2. What happens because of all this? So in the first step, we end up with the two components of the Cheppy net, which is, the θ0 and then θ1, and then the Chebyshev polynomial is a function of the sort of the tweaked Laplacian, which was normalized also by lambda max. And we can rewrite this going back to the original way we defined what the Laplacian was, and we end up with something which looks really simple here. And the final change that has been done here is that you have two parameters, and then those two parameters are also kind of represented using like a single simple transformation. So you only have like one parameter now, and all you have here is now your x is basically, I don't think I explicitly defined it. It was on the slide. So that's basically if you have your node features, if you have a graph with n nodes, your x is the feature matrix. And in this case, it has only one scalar feature per node. And this operation here, if you see, it has the tweaked adjacency matrix and then the degree matrix and your node features. And that is sort of like, we can think of this as in the next one where we generalize it a bit more. So if you assume you have node features at input having C channels, and then you take your theta here, which was just single. Now we inflate it to, so for instance, go from the C features like you would do in a convolution operation. You want to go from an input feature dimension to an output feature dimension. If that is F, we end up with this propagation rule. Now, what is this here? If you see, this is theta, and then X is your node features, right? And then the node features are living in, your n nodes are living in a C dimensional space. And then after this multiplication here, now you transport all these nodes into an F dimensional space in a sort of like, it's a linear operation. So you're basically doing like your linear, your linear layer sort of a thing here. And your adjacency matrix is where basically the neighborhood information comes from. So once you have transported your nodes to this F dimensional space, then you use this adjacency matrix to sum over the different neighbors. So in a CNN or in a regular grid, you assume that you have a constant stride because it's all regular. So now here we need to, for every node, we need to say who the neighbors are, and that's given by your connectivity matrix. So once we have sort of a rule like this, we can stack them into multiple layers and then have nonlinearities and then start doing deep learning sort of tricks. So what happens here is that of course we made these really big simplifications, but by being able to have nonlinearities out here, because here it's a linear operation, but you can also learn a nonlinear feature transformation And then if you have multiple layers, so we may be able to get better approximations, which like a spectral filter would yield you. But here, because it's data driven, whatever helps your downstream task. But this is sort of like how we arrive at the graph convolution operation. Now let's look at this from like a node's point of view, right? So this is, we've been looking at, the regular grid. That's no issue here for this node. These are the neighbors. Now for a graph like this, if you want to look at the neighborhood of node I, and then the first hop neighbors are these blue, and then the second hop are like, 2 edges, 2 hops away, right? So now this, just from the previous expression, if you look at it, you just take your current features or neighborhood features. Let's start from here. So it's an iterative. So you want like a multi-layered, graph neural net. So in that case, you start out with your input features, H0. So now at the first output, then what you get is basically a transformation of all your input features. That was from the slide here, right? We first take the data and then map it to a different domain. So now this can also be done using an MLP. So that's what happens here. And I'm writing out the generalized version. So we take the input and then push it through an MLP. So now the nodes live in a different space, and then we sum over all the neighborhood. So that's your graph sort of convolution operation here. And we can have several of these, and we will look at one of the applications from one of my collaborations next. So yeah, so this is sort of like leading into the idea of we started out with wanting to do convolution on graphs, and then it ends up being neighborhood aggregation, which is, if you also have looked at probabilistic graphical models, which have a lot of inference going on. So there's the notion of message passing. There's this classic algorithm called the belief propagation, which I think is also known as the sum product algorithm, but I like the term belief propagation because nodes are propagating whatever they believe based on their connectivity. And GNNs are sort of generalizations of that. And there's going to be like another example for that to look at it closely. But the idea of GNNs being neighborhood aggregators, I hope is sort of clear going from here. And yeah, if you have like multiple layers, you then get access to information from multiple hops of neighborhood. Just a single layer gives you access to just the first order neighborhood. By stacking, say, 2 GNN layers, then you can hop onto the second order, etc. And depending on your graph and the type of your problem, sometimes you want to go like 3 hops, 4 hops, but you never want to go like really deep, I think, in a neural net, because you end up with problems like over smoothing, that every node gets information from all the nodes, so everybody thinks the same thing. So there's no diversity of opinion, right? Okay, cool. Any questions so far? All right, I shall keep going. So this is just to kind of put like GNN in one up. This is a work in progress, but I think we will be talking to Eric and the team to try and solve some of the issues that we've had. But the key idea is that this is a general sort of holy grail, according to my chemistry collaborator, that you want to give a property and then you want to get a structure out for corresponding to that property, and experimentally doing that is really expensive. So if you can get some simulated data and then be able to learn these mappings using a data-driven approach, it could be really, really cool and useful. So in this case here, the input property is defined using what is called a pair distribution function. And the only extent that I understand is that these are histogram of interatomic distances in your atomic structure. Am I right, Emil? Okay, good. So, and then going from this, you want to be able to obtain these structures. It's a nice sort of a problem. So you have like a property, and then this could be something else also for your domain. And then here we use this as an example. What we end up sort of plugging this into is sort of a conditional variational autoencoder models. Now, could we do something else? Yes, of course. Why do we do this? Because I like VAs. So, sort of simple ideas like that, I think. So what we do here is, let me get on to the model. So it's a classic conditional, variational autoencoder. The conditioning input is your property, which was the PDF in our case, the pair distribution function. And then during training, we give pairs of the structure and the property to the encoder. And then the encoder and the graph, where does the graph neural net come in, right? So the simple idea that structures can be represented as graphs with nodes being atoms, and then attributes, I don't know. So starting from the atomic number to the valence electrons, and we have a lot of populated list of node attributes. And so once we have this sort of setup here, so we train. I'm not getting into explaining a CVA, conditional VAE here, but what we do is we train them jointly, and then at inference, we hope that we have a sufficiently informative structured latent space, which then can take your property here, and then you can obtain not just a single structure, but then a population of structures by traversing this latent space, etc. And does it work? I'm talking here, so it works a bit. So, so what we have here is that these are, I think here are the original structures, and then these are, what the model is able to reconstruct and sort of from the validation set. But the more interesting thing is also that we don't have those results here, but these are simulated property and then structure pairs. But we also have some really small experimental data. And then the model really works well, even on the experimental data. And that was a bit surprising for us because we'd done all the model development on simulated data. So it's I think, really cool. But the more, I think, useful things that we've been looking at is that because it's the conditional variational autoencoder, the latent space has some nice, smooth properties, etc. And we are able to see that not only the structures are clustering according to their types, but we're setting up some interesting experiments where from a chemistry point of view, when you go from one structure to another, there are some intermediate structures, which we are also seeing in the data now when we traverse on this latent space, which I think is a really nice result. So now where does the GNN come in the encoder, right? So where we take the graph, and then we have the node attributes, and then we have the connectivity matrix. And I think I really skimmed through here, but what we ended up doing was, you have like a multiple layers where you transform the nodes. It starts from the input feature space, and then we push it through multiple layers of feature spaces, and then finally you get the latent vector here, which lives in the latent space. Of course, the graph has n nodes, and then it lives in L-dimensional space, and you can do lots of tricks as to how you can summarize the graph. A simple operation like mean operator maybe, or you can also learn another network which can summarize your graph into a latent vector. All right, so that's for node GNNs, as I like to call them, because they are basically explicitly talking between the nodes in the graph neural net. But I think there are some cases where, yes.
So you're smoothing the attributes.
Smoothing the attributes.
Are you assuming that it makes sense to make sums of attributes like atomic number? What does that mean?
Yeah. No. So like one of the base, the thing is, you want to go from. So you have a graph, and then you want to summarize the graph in some way. Yeah. And I think the simplest thing would be to sum over that, but it's no longer just the atomic number, because we've pushed through a few layers of GNNs. The messages have changed, and then the latent vectors no longer hopefully mean the same. But we don't actually do like a summation operation now. We do like a coarsening operation, like a pooling operation, until you end up with like the most representative node for the particular graph structure. I think there's some bit of literature on how you can summarize graphs into latent vectors. Yeah.
Can you explain a bit about how the decoder works?
Yeah, okay, I skipped that part because there's no graph neural net in that, but of course, so yes, so what we do here is, of course, we started out with having like dual decoders, so one to predict the node attributes and then one to predict the connectivity matrix. But I think right now we can actually, because of this type of data that we have, we can predict another property from which we can generate the structure. So it makes our life easier in some sense, because I know in graph autoencoding, that's sort of the big problem, that you can take an input graph and then you can nicely embed it into a latent space. But how do you go from this latent vector into a meaningful graph representation? And there's been some work using recurrent neural nets type of an approach where you start building your structure node by node, etc. But we were able to circumvent that because we were lucky with our type of data. So you can predict another property from which you can get the structure out, but we can backpropagate through that signal, which still informs our, the structure properties. Yeah, so what I was saying was that the node GNNs where you're only aggregating neighborhood, they're very useful, as you previously saw, but there's also some classes of tasks where you're interested in modeling the relations. So the edges, and I think in the mesh cases, there were also cases of where you wanted to collapse the edges and then try to figure out what happens. And then to be able to do that, there's a simple tweak that you can do to the GNNs. It's I think there are like more structured ways of doing this, like in a layered approach. But I think it's nice to just see what happens inside. So you just take your so this is from a node and edge point of view. It's not at the graph level. So at input, you have this node xj, and then you want to take that and embed it into another feature space. And this can be an MLP again. So I think I'm also a big fan of multi-layered perceptrons. So they're like really flexible, and then you can do wonders with them if you use them right. So here again, you can transform the input node features into a feature space. And if you want to represent edges, what we end up doing here is like we look at the connectivity matrix and then just concatenate the features of the two vertices between which the edges are. And so now this concatenated feature space is twice as big, right? Because if you were in F-dimensional feature space, now you are in 2 F-dimensional feature space for the edges. And then you push it through another MLP, which then tries to learn, okay, given these two node attributes, what's the message, perhaps? What's the edge representation here? So, and going back from the edges, you can simply do a summary operator here. So you can sum over all the edges for a particular neighborhood and then push it through another message passing an MLP, which then figures out, okay, given all these messages and this neighborhood, what could be the message. So now this is just a 2-layered case. And then finally, you can end up in something like an edge space, and you can decode this into, if you want to make like link prediction, or if you want to do graph refinement. So if you have to keep the edges or not, then you can go from this edge space and then collapse the features into one vector, for instance, and then do a sigmoid. Then you get like a probability of edge existing or not, etc. So this is used extensively in sort of link prediction type of tasks. But what I really wanted to point out here is that we have these two types of messages now. So, the nodes to edges and then edges to nodes. And this, as I already hinted before, is kind of reminiscent of lots of models which are in probabilistic graphical model literature. For instance, if you have something like a Markov chain, like a first order Markov chain, then you can solve, solve for the marginal probabilities or the posterior densities using a Kalman filter, or you can do Kalman smoothing, etc. But they're really nicely defined for those types of problems where the nodes actually, talk to each other by passing, their beliefs. So like the conditional probability estimation. So then I already mentioned the sum product algorithm or the belief propagation. So now you can use this also to factorize. So now, for instance, if you have a factor graph, I think that's the closest one to something like having a GNN with edge and node representation. Because if you have like random variables, U, W here, and then if you have the edge here between, okay, let's look at U and X. So the edge here has basically a factor which has all the variables in. So that's sort of the factor graph. And then these message passing algorithms have been used quite widely. And then I'm a little disappointed that we don't use still a lot more of these because they can be really efficient in solving. And that's also perhaps because we no longer do a lot of probabilistic graphical models. And then we treat everything, we want to do the likelihood estimation in most cases. But so we also, if you are into image analysis, conditional random fields, Markov random fields have been around, and then these can also be optimized for using approximate inference methods. Something like a mean field or variational inference can be deployed in these cases. Now, all this to kind of say that, can we then formalize the connection between, GNNs, which are also passing messages, right, between nodes and then edges and then edges and then nodes into these rich classes of, message passing algorithms. And I think we tried doing this in one of our works, but it was more like a empirically proven solution. But last year there at NeurIPS, there was a paper called Factor Graph Neural Nets, which basically use GNNs to perform the max product algorithm, which is just another variant of the belief propagation algorithm. And I think that's pretty cool, because now we get access to sort of like multiple domains of literature to kind of improve our inference on our models. So I have another 6 minutes. I will very quickly go through this last bit of work that we wanted to talk about, where we use GNNs to do mean field approximation. And yeah, so what is sort of the task? I'm going to have to skip like the medical literature here, but the key idea is that, so I was working with, or I have been working with volumetric CT images, and then we want to perform airway segmentation, so segment the trees of airways. But one of the issues that with all the baselines that we were looking at and other models we were looking at was that we would lose out a lot of the small branches, because a little bit of noise down the airways, when the airways become really small, would sort of obfuscate the remainder of the airway, and then these methods would be looking for something that is connected, and then as soon as you would encounter a discontinuity, you would lose out a lot of the rest of the branches. Now, of course, this could have been done in very many ways, which we also tried. But in the end, what we ended up doing was to formulate this as sort of inverse of link prediction problem, which is graph refinement, we called it, which is basically you start out with like an overconnected graph, and then you want to throw away all the edges that are not relevant for your downstream task. And this so that's basically the idea here. So what we then, I'm going to talk about these two very quickly, where the model, so don't worry about these layers. So they get input features and then input adjacency matrix, and then you want to be able to refine it in a way that your final output looks like the skeleton of the airway tree that you have, perhaps with attributes from which you can reconstruct the original underlying airway tree itself. So to be able to do that, of course, you want to now model this in a probabilistic setting. And how do we do that? We model the connectivity as like a Bernoulli random variable, so either 0 or 1. And then, so once you aggregate these into a joint variable, then you get, so the instances of this probability density is going to be an instance of an adjacency matrix, meaning an instance of what possible skeleton that you would get. Now that's the point here then. So what we are then interested in is this posterior, which is over this joint connectivity matrix conditioned on the graph attributes, which are your input node features and then the adjacency, the input adjacency matrix. And of course, yeah, I mean, this is where a lot of Bayesian people get taunted that we can't solve this. So we approximate this by going to the, looking at you're noticing that this is proportional to the joint. And then from here, we start talking about, how this is sort of the free energy formulation. And that's what we end up doing. So you can do something like, you look at the joint and then you can write this out as the free energy formulation, from which you end up with, you can factorize this into very many terms, but we stop just with two types of potentials. One is the node potential, and then the other is edge potential. And this we hypothesized would be sufficient for our downstream task of doing, graph refinement. And again, like I just want to emphasize that there are two types of messages. Then, there's node messages, and then there are like edge messages, which hopefully, we see the connections going forward. Yeah, I have grayed these out because we don't necessarily want to get into these details, but then, we have. We specified the model to figure out what these node potentials should be, what these edge potentials should be. And then we end up with like a few, cases which encourage, behavior or discourage behavior, depending on if a particular node is on the skeleton that you're interested in or not. Once you have this, then we do mean field approximation. So this is a simple case where you just take like a high dimensional joint distribution, which you can't factorize. And then you say that, which is, hard to optimize. Then you say every node is independent. And then we try to, optimize them iteratively. And there's, again, a lot of established algorithms here. And this gives a nice property here, right? So with a lot of deep learning models, you don't get any guarantees to optimization. I mean, of course, you're always ending up in some local optimum, but you don't know if you can do better or not. But once you are in something like a variational inference framework, you can always optimize the evidence lower bound, and then you can, do restarts or whatever, and then know if your solutions are better than before. So you get a bound on the evidence lower bound here. Okay. So anyway, so once we have this, yeah, okay. So because of the model that we specify, don't again worry about this part, but all it is doing is message passing, because mean field inference is also another framework where you can iteratively, update your states. You start out with a particular belief, and then you iteratively optimize your way out until your models have, your nodes have the marginal probabilities converge to what the ground truth are. I mean, more or less. So we take this iterative algorithm, and because of this type of a structure, we take the iterative, so each iteration, and write it out as a layer in a neural network, which has like handful of parameters. So instead of having like T iterations, it becomes T layered mean field network with only about 46 parameters. And then you can learn those using back propagation, because we have some labels for our data here. Now, the thing with what you can do with a graph neural net is you don't have to do this painstaking specification of what the node message should be, what the edge message should be. If we parameterize that with a, something like what we saw before, like using MLPs, and then given sufficient data, we may be able to, solve this problem. And this is where I said we don't prove it that if we get a bound on the evidence on the log likelihood or not, but we do get like good results. And I'm going to again skip through it, except to point out that even without specifying that we are looking for a tree type of a structure, because in the mean field case, we do encode behavior which encourages tree type of behavior. But the GNN is able to sort of relatively do better. And then this is what the final reconstruction would look like. We get the skeleton, and then we also predict on like just property like the local radius, so that you can reconstruct something like an airway tree from these skeletons. And like, okay, yeah, we have these baselines. There's also for UNet. So all, if you notice here, so the borders are where there are lots of missing branches. And for the mean field and then the GNN, there are still some problems, but then when we look at it, the most sensitive ones are still better retrieved with a model like the GNN. And with the mean field, we did not, looks like, right, we did not specify these potentials which would discard. I mean, we could do a bit of post-processing here, but just the output of the result we don't discourage these behaviors. So we do end up with a few of these, unrelated predictions for an edge. Yes, so like I already mentioned, this is a really nice paper if you're into coding theory and have done a bit of belief propagation, etc. So this was at Neurich last year. I would encourage you to take a look and see how we can do more of probabilistic graphical models driven GNNs also. And in a non-probabilistic graphical model setup, there's another generalized message passing algorithm paper from 2017 by Gilmer et al., where they also take, by now, I don't know, there must be like 500 variants of GNNs, but they all would fit into something that they formalize here. So you just have like two things going on. You have like a message update and then your status update. So, and then depending on what types of messages are sent, you would end up being a different type of a graph convolutional network. Like Rasmus also showed, PyTorch geometric has like tons of these, GNN layers now, but I think you might be able to just think of them as special cases, and that's what they try to do here. Yes, so in summary, we started out trying to do convolutions on graphs, but then we realized, okay, you can't do it in the spatial domain. You have to go to the spectral domain. And then we ended up doing the Chebyshev approximation. So you do get like a spectral variant of graph convolutional network. And then we make this drastic assumption that we are going to use only the first two components. And then this becomes, I did not specify, it becomes a spatial, graph convolutional network, because you still are, operating, you don't need the Laplacian there. You only are using the adjacency matrix. So it's no longer, in the spectral domain, it's a pseudo spectral, GNN, if you'd like to think of it. And yeah, okay, I did not have time. I had slides for this, but then I did remove this. One of the simple things with the early on GNNs were that like all nodes contribute equally to your status update. And that's not maybe useful. And that's where, we started out with the very simple notion of, you want to weight the messages that you get so that you do a weighted update. And this has become, graph attention networks. And now there's also, I think concrete proof which tie them to be, generalizations of transformers that we are looking at in the literature these days. All right, so that's my talk. And I think PyTorch geometric was already mentioned, but if you might also want to check out DGL, I think it's Deep Geometric Library, I think. But then they have really nice tutorial section where, authors of the papers actually make tutorials for their versions of the graph neural nets. So I think that's a good one. But if you're also moving away from PyTorch to using JAX, then DeepMind also put out a JAX-driven graph library called JGraph. And some bit of pitch also. So we've been working on, carbon footprint aware deep learning, because we are causing substantial amount of, overhead by training our models. So if you'd like to first be aware of what you're doing and then think about what you want to do, try our tool, Carbon Tracker, which we put out last year, and it has garnered a bit of attention. It not only tracks, but you can also predict. So you can actually use it to design your hyperparameter tuning, because you can use this prediction to optimize what parameter space you want to go in and not. So that's not in the tool. We are working on it. But I think, yeah, that's all from me.